Okay, thanks everyone for coming to our seminar. So today we have Bahareh Rahmati. She's an enthusiastic PhD candidate who started her program at the School of Computer Science here at Windsor in January of 2021. Her research is in the field of data science and AI with a focus on graph-based recommendation systems and explainable AI. And she currently has published multiple papers in top-tier conferences. So Bahareh, please take it away.
Hello, everyone. Welcome to my presentation regarding enhancing palliative care through social network analysis. It's a study on social isolation detection and recommender systems. First, let's see what's the difference between a network and a social network. A network is a system of interconnected entities. It can be any interconnected system like computer network, social network, specifically focuses on a social actor and the relationship or interaction between social actor or nodes. But what is social network analysis? Social network analysis is also called network science. It's a field of data analytics that try to understand the social structure, the relationship among teams or network of individuals. There are two key components in every social network, the actor and the relationship among actors. These actors can be individuals, organizations, or entities. And we can have different type of relationship like friendship, communication, or collaboration. The question is why social network analysis is such an important research topic? Because it helps us to identify the individual or teams who play central role in network. Once we gather some tweets from Twitter regarding COVID-19 vaccination, we ran 6 well-known classifiers on the data, and we classified them into fake and real tweets. Then we did community detection on fake tweets. I mean, we identified the group of people or the communities who spread fake news regarding COVID-19 vaccination and their leaders. This is one of the applications of social network analysis. Another significant application of social network analysis is to identifying the structural holes in a network, the isolated individual. By isolated, I mean the individual who has less connection in comparison with the rest of the network. This is one of the use case. Social isolation detection in palliative care using social network analysis. I will elaborate on it in next few slides, but before that, let me familiar you with one of the most famous applications of social network analysis, which is recommender systems. They came into being in 1990 when we want to buy an item from Amazon, whenever we want to watch a movie on Netflix, it's the recommender system that helps us to identify a good choice. In its common formulation, recommender task is to predict or estimate the rate for unrated items for the user, or sometimes it's finding the relevance rank of item in comparison with rest of the items in the system. And after finding the rate for that item, the recommender system will recommend us the item with the highest estimated rating. It's a problem-rich research area. It has lots of application, and although there are lots of advancement in the field, the recommender systems can be more effective and applicable for a broader range of real-life applications. Nowadays, we can find a recommender system in almost everywhere. We have electronic government recommender system. Once I was part of a project with IRCC, Government of Canada decided to design a recommender system for newcomers from the time they arrive in Canada until they settle down. For instance, if they want to have their driving license, if they want to go to an English institute, it's the recommender system that suggests them the best way. I mean, in order to do the task, the way with least cost and in shortest amount of time. We have electronic business recommender system. E-commerce is the most famous one, like Amazon. E-library recommender system, e-learning, e-tourism, e-resource service, and nowadays e-group activity recommender systems. The traditional type of recommender system just suggests an item for an individual. But now, if for instance, you and your family want to watch a movie on holiday, it's the group activity recommender system can balance the expectation of different people in group, and based on the whole group, it can suggest an item. These are the famous type of recommender systems: content-based filtering, collaborative filtering, and hybrid recommender system. Regarding content-based filtering recommender system, as the name suggests, it considers the content of the item and the user profile. And based on their similarity, the system suggests an item to user. For instance, if you ask me who is your favorite director, filmmaker, I would say Christopher Nolan. So if I have previously watched a movie by this director, like Inception, it's probable that the system suggests me another movie like Following. However, it's not that famous, but is directed by Christopher Nolan, and it is a good choice for me. Mostly, in order to represent the content of item and user profile, we use term frequency, inverse document frequency in content-based recommender systems. Term frequency is based on the frequent word in the documents. Of course, we are not looking for the keyword like A and D. They are repeated in all the document, and we cannot distinguish between document using such keyword. That's why we use inverse document frequency, which is the log of total number of the document to the document that contains the keyword NI. Times frequency, terms frequency times inverse document frequency will give us the keyword weight. And after representing the item and the user profile based on term frequency and inverse document frequency, the recommender system consider the utility of item for that user and suggest the item with maximum utility. There are some limitations regarding each type of recommender systems. For content-based filtering recommender system, they suffer from over-specialization. It means that the system consider the similarity of the item with the user profile, and it cannot suggest something novel. Also, if a user is new in the system and the user has not given sufficient rate to the items, the recommender system cannot be that accurate. And if two items are represented by the same set of features, the content-based filtering recommender system cannot distinguish between the items. We have a collaborative filtering recommender system as another type of recommender systems. Collaborative filtering recommender system can be user-based or item-based. It can be based on the similarity between users or similarity between items. If you look at the picture in the right, if there's a person in the system that has bought a pizza and a salad, also I have bought a pizza and a salad. If I buy a drink, it means that it's probable that that person wants to buy a drink. That's why the recommender system will suggest the drink to that user. So the rate of an item for a user in a collaborative filtering recommender system is based on the aggregated rating of its neighbor users, its similar users. We can have different type of aggregation function. It can be an average, it can be weighted sum. You can see the aggregation function in the right. Totally collaborative filtering recommender systems can be memory-based or model-based. Memory-based are heuristic algorithms, and model-based use machine learning and deep learning technique as the approach. Regarding the limitation of collaborative filtering recommender system, like content-based recommender systems, we have new user problem if someone is new in the system and that person has not given sufficient rate to items, so the system is not that precise. Also, if an item is new in the system and the users have not give rate to that item, the system cannot suggest the item to users. And if the number of rating that already exists in the system is very small in compared to the number of rating that needs to be predicted, we call it data sparsity, and the system is not very accurate in this case. In order to alleviate the problem regarding content-based and collaborative filtering recommender systems, we have a new type of recommender system, which is called hybrid recommender systems. There are different ways in order to make a hybrid recommender system. First, to implement the collaborative and content-based filtering separately, then combining the results. Another approach is to incorporate some content-based characteristic into collaborative filtering and vice versa. And the other approach is to construct a unifying model that has both the content-based and collaborative characteristics. Mostly hybrid recommender systems are better than pure content-based or pure collaborative recommender systems. If you remember, I talked about one of the application of social network analysis, which is identifying the isolated individual. This is one of the use case, social isolation detection in palliative care using social network analysis. Social isolation is a public health problem. It can lead to lots of mental and physical health diseases like diabetes, heart disease, lack of self-esteem and cognitive abilities, suicidal thoughts. Older people and palliative patients are more vulnerable due to outliving family and friends, life-threatening illnesses, disability. The rapid growth of this aging population highlight the importance of the issue and even make it more critical. The situation gets worse, especially during COVID-19 pandemic. This research was done during COVID pandemic. It was very severe for those who are isolated. The adverse effect of isolation, if is not detected and tackled, not only will affect the individual, but also the whole society. The government should suffer financial burden in order to provide the resources or facilities for palliative patients. There's an old saying, prevention is better than cure. The authors in this paper have proved that it is true for isolation as well. I mean that if we detect the factors that put people at risk of isolation and avoiding them can be a great help. A relationship between an individual and his social group, the strength of the relationship, age, marital status, chronic disease are some risk factors for palliative patients. Although the research is of vital importance in this field, but there are not lots of research. That's why we decided to design a framework in order to identify the isolated node using social network analysis techniques. Not only we consider the structural characteristic of the network, but also the individual's behavioral feature. And we created a framework. We evaluated our framework using some real-world data set as well as some synthetic networks. We modeled the social network into a graph represented by G as a set of nodes shown by V set of edges and the weight of the edges. W is the weight. It's a real number between 0 and 1. It shows the strength of connection between each pair of nodes. The set of nodes are the patients and their care provider. They can be formal or informal care provider. For instance, regarding the formal care provider, it can be a nurse or physician. For informal care provider, like a family, like a friend. Also, we considered a set of abilities for each patient, like walking, speaking, talking. Each ability can have 3 values. 0 means that the individual cannot do the task independently. 0.5 means that the individual can perform the task, but with help from others. 1 means that the individual is able to completely do the task independent. Also, we consider some demographic feature like age, marital status, and quality of life index. We converted the problem of detecting isolated nodes in a network as finding outlier nodes in the graph, considering the structural characteristic of the graph as well as the attribute of the nodes. These are some related work. In first paper, Dr. Moradianzadeh has designed an algorithm for identifying the isolated nodes using the structural characteristic of the network. Second work is also an isolation detection algorithm using data analysis techniques. The authors have also developed a mobile application for it. The third one, investigate the impact of COVID-19 on social isolation for Twitter users. The last one is also similar to the third one, just they consider some factor that affect the isolation, like the time and the physical space. Also, these are 2 related work considering finding outlier in the graph. The first one consider using support vector machine SVM algorithm. It is used to separate one class of observation from the other by using a hyperplane in multidimensional space. Also, the algorithm can be used for one class problem. We can teach the algorithm what is normal data, and if we show a new data point, it can recognize whether it's new or not. That one is also a similar work. It enhanced SVM somehow. The authors believe that it has better accuracy and it doesn't need manual parameter tuning. Here's the framework of our algorithm. It consists 5 phases, creating social graph. By assigning ID to each entity, we link it to its care providers. Then we add some attributes like communication and ability indexes. We add some demographic information like age, marital status, and we create the feature matrix. And our algorithm identify the isolated nodes. And finally, we evaluate our work using some real world and synthetic data. I will elaborate on each of the phases in next slides. For creating the social graph, we designed the node ID labeling protocol. It consists 10 characters. The first character shows whether a patient is a client, whether an individual is a client, informal or formal care provider. The second character shows, for instance, if it is a formal care provider, whether that person is a nurse, a physician, a healthcare worker, or a health agency. And regarding informal care provider, we have friends, family, and community. The next 3 characters is the ID of the registration center, and the rest are the member ID. Not only we assign a unique ID to each client, but also to each entity in the network, so that we have the big picture of the network. The unique ID enable us to map the network into social graph. We model the work using undirected weighted graph. The nodes are social entities in the graph. The edge shows if there's connection between pair of nodes. We used edgeless data frame to store the graph information. We have 2 columns, the source and the destination. Source are the patients, destination are those who have interaction with the patients. We define weight for the interaction. Weight is based on frequency times quality. Frequency is defined as a number of times two individuals interact with each other, or an individual have interaction with formal or informal care provider. Quality is the duration of each connection based on hours. For instance, if an individual visits her family 2 times a week and each time for 20 minutes, the frequency is 2 and the quality is 0.33 because it's based on hour. Then we define the community index as the estimation of the level of connection for each patient is sum of the weight of its edges. We have also ability score. Ability score is a sum of the score of the ability for patient. The ability is any task that the client's score is greater than or equal to 0.5. This ability is its complement. Every task that the client score is less than 0.1. 0.5. Ability index is a sum of ability score plus a constant value times the number of the abilities. We define this constant value so that we can give weight to the cases that an individual can perform the task independently. Besides the network structure set of abilities, we define some demographic abilities such as age, marital status, and quality of life score. We add communication ability indexes to form our feature matrix. Our feature matrix is an M by M matrix and is the number of clients, M is the number of features. Our goal is to identify the outlier node in the network. The outlier means that those who behave differently from the norm of the society. The algorithm work considering these steps. At first, calculating the average and standard deviation for each feature, then making a new feature matrix. If that feature is one standard deviation below the average of that feature will be 0. Otherwise, it is 1. We extract the norm of the society, considering a threshold, and we calculate the Hamming distance of each individual with the norm of the society. If it is one standard deviation upper than the norm of society, we call it an isolated individual. Finally, we return the isolated individuals. Here's the pseudocode of our work. The input, as I mentioned, is an N by M feature matrix, and the output is a list of isolated nodes. We evaluated our work using some real-life data. It's a joint work by Windsor, Essex Compassion Care Community. We had 1,000 palliative care clients. Survey that are filled in 2017. We randomly selected 10 clients and manually labeled them in order to make the grant root data set. The survey are self-reported questions. It contained the information regarding the informal and formal care providers, also the frequency and duration of the connections. Also, we tested our work using some synthetic network. We created some synthetic network with 300, 500, and 1,000 nodes. We used LFR benchmark for creating those networks. The average degree for each node is considered to be 15. Our minimum community size is 10. Our maximum community size is 50. And we consider the density of the community age to be 0.2. The ability that we extract from the paper consists moving, hearing, talking, seeing, bathing, grocery shopping, dressing, and going out. We set K to be 2 in all the experiment. And the feature that we extract from the survey consists life satisfaction is a score in range 0 to 5, marital status, birth year, and living alone. We used Python programming language with NetworkX and PyWiz libraries. All the experiments run on a system with 64-bit operating system, 4 GB RAM, and CPU Intel Duo. We use also Flask and D3.js to visualize the network. Here is the visualized network. You can see 216 nodes here. The dark blue nodes are the patients, the oranges are informal care provider, and the light blue nodes are the formal care provider. The higher the strength of connection between each pair of nodes, the bolder the edge. We define for different scenarios in order to evaluate our work. In first two scenarios, birth year, marital status, life satisfaction, living alone, and communication index and ability index was the feature that we considered. In first scenario, the threshold is set to 50%. In second scenario, the threshold is 60%. Also, in next two scenario, we removed the living alone feature from set of features because somehow we have calculated when we were calculating the communication index, and we run the algorithm with 50 and 60% threshold. We use accuracy, precision, and F1 score as our performance metrics. This is the result of our experiment. When we ran the algorithm on real-life networks, the better result was gained when we set the threshold to 50%. Also, when we decreased number of features from 6 to 5, the effect of threshold was negligible, and the algorithm identified more isolated individuals. In order to compare our work, we used SVM algorithm for comparison. We set the gamma value to 0.001. We used SVM via RBF kernel, and we set the threshold to 50%. The results showed that the SVM algorithm result is highly dependent to predefined parameter of nu, and overall, our algorithm perform better in comparison with SVM on a real-life data set. Also, we made some synthetic network with 300, 500, and 1,000 nodes. We consider 5 and 6 feature. Because we didn't have any ground truth for our synthetic network, we randomly selected some isolated and non-isolated nodes and compared their communication and ability index values. On average, the communication index of non-isolated node is 6.7% higher than the isolated node. And the ability index of non-isolated node is 12.4% higher than the isolated nodes. For testing the algorithm on synthetic data with SVM algorithm, we set the new parameter to 0.1 and 0.2. The results show that no matter how many features we have in the system, we will have the same result. So if we create a graph with 1,000 nodes and we set nu as 0.1, the algorithm return 98 individual as isolated nodes. When the features was 5 feature, and when we consider 6 feature, the algorithm returned 99 isolated individual. Totally, our algorithm is not that dependent to a predefined value. So it has also lower communication and ability score in comparison with SVM algorithm. It performed better than SVM in different scenarios. For future, we aim to design a recommender system for palliative patient. Each patient has a set of capabilities, has some requirements, also has some goal to achieve. In order to achieve the goal, there are some events and practices that help the user to achieve the goal. We aim to make a sequential recommender system with deep learning approach because sequential recommender system can consider the temporal order of user item interaction. They are good for scenarios when user exhibits sequential behavior. As in our work, some resources are a prerequisite for other resource, and we want to estimate the evolution of user item interaction over time. We think that our sequential recommender system will lead to better accuracy and more user satisfaction. Temporal dynamics, data sparsity, cold start problem, and long-term dependencies are our potential challenges. And we aim to consider mean reciprocal rank, hit rate, and accuracy as our evaluation metric. Mean reciprocal rank evaluates the success of recommender system in terms of relevant rank of item in top N recommendation. Hit rate is based on success of our recommender system for relevant item in top N recommendation, and accuracy is based on the fraction of user item interaction that the recommender system can identify correctly over all the interactions. This work was partially funded by MyTax, and it was a joint work with Windsor Essex Compassion Care community. These are the references. Thank you for listening. If you have any question, I do welcome your questions.